In this video, we are going to understand when do rational numbers. We all know what rational numbers are. Rational numbers are numbers which can be expressed in the form p upon q, okay, where p and q are integers and q is not equal to 0. So when can we say that a rational number will have a terminating decimal expansion? So whenever you expand a rational number, okay, can by looking at it you tell us whether or not it will have a terminating decimal expansion? It will have a terminating decimal expansion, or it will have a non-terminating but repeating decimal expansion. So let's say, for example, you are given a number 5 upon 10. We know 5 upon 10 can be written as 0.5, right? Now in this case, if you see the decimal expansion, it ends at a particular number, so it is terminating, as we call it. As against this, you could have some other numbers where this termination doesn't happen. So let's say, for example, if you have to divide 100 by 3 or 33, right? You will get 3, right? That gives you 99, 1.030303, and this will keep on repeating itself. So these are called non-terminating because they are not terminating. After the decimal there is no 0 or no end to it. And repeating. Why repeating? Because if you see here, 03 is repeating itself a large number of times. Non-terminating, repeating decimal expansion. So can I say by just looking at this number whether or not it will have a terminating decimal expansion? And that brings us to this theorem that we have over here. Now what this theorem says is that a rational number with terminating decimal expansion, which is something like what we had over here, can be expressed in the form p upon q, where p and q are co-prime, right? So what that means is, if I just look at this particular thing, are 5 and 10 co-prime? The answer is probably a no, because 5 and 10 can also be divided by 5. So it could be 1 upon 2, right? And the prime factorization of q is of the form 2 to the power m, 5 to the power n, where n and m are non-negative integers, right? Let's understand this a little bit more in detail. And for that, I will take an example. And thereafter, we'll come back to this concept of 5:10, which I have reduced to 1:2, okay, and explain this concept in relative to this particular one as well. So let's say, for example, we have a number 0.875, okay. Now, if I have to convert this into a rational number, I will write this as 875 upon 1000. Simple. I've just added 30 and removed this decimal from here. Or in other words, I can write this as 875 upon 10 to the power 3, right? So if there is a rational number, okay, which has a terminating decimal expansion, okay, so if we talk about this rational number, this has a terminating decimal expansion because it just has 3 words. After that, there is nothing, right? Then one thing which is sure is that the denominator of this rational number will be a power of 10, right? So if a rational number has a power of 10, then we can say that this could be a terminating decimal expansion. Now by its very nature, if you write 10 in terms of prime numbers, 10 can be written as 2 times 5 because these two are the only co-prime factors of 10. What we can also say is, in that case, that any terminating decimal expansion rational number will have 2 times 5 to the power n. This n could be anything, or simply 2 to the power n times 5 to the power n, right? Now, effectively what will happen here is that if you just cancel out, so what we do is that whenever we have this denominator, we just express the numerator as well as a part and parcel in form such that it is a factor of only the primes. So if I have to write 875, I can write that as 5 times 3 into 7. right? When you do a prime factorization of 875, you get 5 times 3, 5 to the power 3, okay, times 7. Sorry for the misspelling that I did. And in the denominator, we have 2 to the power n. 3 is the power, so 2 to the power 3 times 5 to the power 3, right? When you cancel these two out, you get 7 upon 2 to the power 3. But since the denominator has to be mentioned as a power of 2 and 5, so I can just simply write this as 5 to the power 0, which is nothing but 1, right? And there comes the theorem into practice, the one that we just saw. Now look at this in that context. Rational number with terminal decimal expansion can be expressed in the form of P upon Q. What is P upon Q in this particular case? P upon Q is this, okay? Or simply, if we would have looked at this, 7 to the power 2 to the power 7 divided by 2 to the power 3, where P and Q are co-prime, okay? Now if you notice, 7 and 2 to the power 3 are co-prime, right? And Q is of the form 2 to the power m divided by 5 to the power n. Now Q in this example is 2 to the power 3 into 5 to the power 0, right? So m over here is what? It's 3, because 2 to the power m and 5 to the power n. N in this case is 0, which is this, right? So if you can express a rational number in this form, right, which is what we spoke over here, such that P upon Q, such that Q can be written as 2 to the power m times 5 to the power n, right? And whatever is this value, the P and Q themselves are co-primes, right? Then we can say that a rational number, a given rational number, is actually a terminating decimal expansion. It follows that if it cannot be written in this form, then we can easily conclude that the rational number does not have a terminating decimal expansion. It will have a non-terminating but repeating decimal expansion, right? Something which we saw over here. In the case of 100 is divided by 3. We'll look at one or two of the problems in the next video relating to this particular concept.